Well, hello and welcome to this workshop. My name is Víctor. I'm happy to be here with you. It's okay. You can hear me, right? Or okay, good. So in this workshop, what we're going to do is like how to build like budget-friendly ground stations for low Earth orbit satellites. So yes, we have the agenda. We will cover a little bit of an introduction about myself, what I do in my current role at United Airlines. The reason why is this workshop happening here at DEF CON, and some basic concepts that you should know before we take go more in deep about the ground stations, like about satellites, and then we go with the hardcore of the workshop that is about the ground stations. We will cover antennas. We will do a lab of antennas, the kits that you already have. We will be the ground plane antenna with the kits. We will cover also some basic concepts about receivers, and then we will do some lab testing also on RTL-SDR. And we will cover also software that is able to demodulate and the signals that we will use later on, right? We will use SDR++ and Gpredict for tracking satellites. And we will finish with some kind of demo, if the internet here is fine, in the ground station that I have back in my home in Florida, where we can try to, if we are lucky, see some kind of signals from the International Space Station or any satellites that are passing through that location. And we will finish with expanding ground stations. So if you like the idea of the ground station and how to expand it, like we can see other type of architectures and more resources that we can use for expanding it. So in this workshop, we're going to need like a laptop or internet access. If you don't have it, it's okay. But if you need internet access, if you go to wifirec.defcon.com and you create an account, you download your certificate. It's pretty straightforward. Follow the instructions. As we said in my home country in Spain, y aburres. So you just go and follow the instructions, right? To have the internet access. All right, so just a little bit about me. I am Víctor Fernández Minguillón. I'm father of 3 children, so pretty busy because they are very small. And I have 6 years of experience in offensive security. I'm currently a senior red team analyst at United Airlines, and I'm pursuing my master's degree in cybersecurity, where my background is in aerospace engineering and computer science too. If you want to follow me on social media, is where I post like my relevant data, like information about projects that I work on or anything. I use Twitter and also LinkedIn for sharing that. So let's get started a little bit. What is this workshop for? Well, the objective is budget-friendly, around $100 like ground station, so everyone can being able to, and it's very affordable. But the reason why this workshop exists is because I submitted a talk to a lessons learned when I built my ground station back in a couple of months ago, right? That is the picture that you see here in the top left corner. So I wanted to share that knowledge with the rest of the people, so we can create a more environment and a more ground station, so we can receive or we can collaborate to with the knowledge of like different like satellite signals and see how they right. And in the bottom is what is inside actually in the workstation. So yeah. So let's go for a little bit of basic concepts about like satellites here. So this is my definition of satellite. So probably it's not the best one, but what is a satellite? A satellite is an object, typically a spacecraft, placed into orbit around Earth that provide different services. So these services, the type of services could be satellite TV, like the one in Astra 1C, weather information with an OA-18, for example, navigation support and mating safety communications, like in Marsat, or everyone knows about Starlink, so internet service with Starlink. And my favorite, that is like university research in form of CubeSats that can are deployed there in the space. So since 1957, when Sputnik 1 was launched by the URSS, more than 15,000 satellites has been put in orbit, of which around 99,000 of them are currently active in May of 2024, right? Based on like the Crossfinger nanoavionics block. So going a little bit deeper about satellites concepts, the most simple satellite must have at least the following elements. The structure that is charged of giving mechanical structure to the satellite, electrical and power system, or EPS, formed by the solar panels, batteries, and electronic controllers, the attitude and determination and control system, or ADCS, that are computers that control the altitude, the attitude and the telemetry of the satellites. And then we have also the communication system formed by UHF or VHF radios to receive and transmit commands from or to the ground stations, and antennas that we allow the downlink to the ground station or the uplink to the satellite. And finally, the payload, that is like a bunch of sensors, like cameras or IR, magnetic field sensors, among others, that are going to help with the mission of the satellite. So depending on the services provided by the satellite, there are different type of orbits that aerospace engineering decided to put these or allocate the satellites, right? The LEO orbit, that is the one that we're going to focus today here, are orbits where the satellites are between 140 kilometers and 900 kilometers above the Earth, and consequently not always visible to the observer, but provide several windows of visibility every 24 hours. So we have chances to see and receive information from them every day, right? The next one that we have is the SSO, or synchronous orbit. It's a specific type of LEO orbit that that travel over the polar regions, right, and are synchronous with the sun. That means that they're always synchronized and always be in the same fixed position in every single time when they rotate against the Earth. For example, is when we put in an orbit that we want this satellite to be at noon in Vegas, so we can have at that time that tracking, right? Then we have the MEO, or medium Earth orbit, that comprise a wide range of orbits between the LEO and the geostationary orbits, right? And the most famous satellites that are in this MEO are like satellites for navigation purposes, like GPS, or the Galileo, the European Galileo system too. And then we have the GEO, or geostationary orbits, that are orbits that circle the Earth above the equator from west to east, right, and following the Earth rotation. So taking 23 hours and 56 minutes and 40 seconds to by traveling the same rate as Earth. So is going through. They go with a speed of 3 kilometers per second, where it seems to be always and constantly seeing the same area all the time, right? It's important because these type of orbits are used for satellites that need constantly stay constantly above the Earth and one place over the Earth, right? So such as telecommunication satellites, right, where the way that the antennas can directly only be pointing to the satellite and don't have to move, right? And or for example, whether satellites where they need to know and manage one area in particular to see what are the trends of that weather area. And let's continue a little bit more with a little bit more in definitions with ground stations, right? And a good and simple ground station definition will be the equipment required in Earth to communicate with a satellite or a spacecraft. So for the reception of satellites signal, we need the following components: an antenna, a receiver, and a software to tune the receiver, to modulate the signal, and decode the information. Well, I said that this will be a kind of friendly way budget workshop, right? So this is the Apollo mission ground station. So it's actually not modern, and probably not very cheap. So actually the components that we're going to talk about today is these three here. We will cover about like an antenna, a ground plane antenna, an RTL receiver, and the software that can help us understand satellites and radio signals too. So let's start with a little bit more definitions. I know it's quite a bit, but definitions with what is an antenna, right? An antenna is an electrical device made by wires or rods with different sizes that converts electromagnetic fields or radio frequency waves into electrical current or vice versa. This electrical current is connected to the receiver, where it will be managed, and we will see, as we will see later, right? And the key parameters of the antennas are the following. So each antenna must be designed for one specific frequency band, as the dimension of them are actually directly related to the dimension of the antenna, right, or the dimension of the rods or the wires. So, for example, the dimensions are proportional to the wavelength, and the wavelength of called lambda, that is what we have here, the lambda, equals like 300. Divided by the frequency of like the resonant frequency, where 300 is actually like the speed of light, 300,000 kilometers per second. Depending on the type of antenna, right, numbers of elements and four-factor antennas exist a concept exhibit a gain pattern that maybe even favors some directions and versus others, either in azimuth or in the azimuth is the ground plane, the horizontal plane, or the elevation plane. That is the image that we here see with the red and blue graph. So actually in the diagram, the red line shows the horizontal azimuth and the azimuthal parent. And you will see the is equal in all the directions. That is actually giving us very good information about that. And while the blue line represents the gain pattern in the elevation process, where the gain is reduced with the increased elevation. The colorful pile of donuts that we see there is like the 3D representation of the diagram of radiations. So, and also properly designed antennas presents in their connector a characteristic impedance, or C, right, that needs to be equal of the impedance of the transmission lines, and equal also on the receiver input impedance to maximum the energy efficiency transference. So LEO orbits satellites have passes over the ground station. That is like we will be like just in the middle of that, from different azimuth directions, and the simplest antenna must have an omnidirectional azimuth pattern, and ideally omnidirectional gain pattern. But that only gain omnidirectional pattern in the elevation is made by different form factors of the antenna. So in order to get that azimuth in omnidirectional pattern, there are several options. There's a different type of antennas that have been built for ground stations. The turnstile or cross dipoles with reflectors antenna, the Gpredict, that is like two metallic circles crossed with two rods as reflectors, and a quadrifilar antenna too, and finally the simplest one, that is the one that we are going to build, the ground antenna. The tables here shows you a little bit of information and a comparison between all these different four antennas, while the three first ones are polarized in right-hand polarization when the ground plane is linear. So as you can see here, in the gain in 15 is actually good in ground plane. So that means if the azimuth is like around from 0 to 15, it's good to have a ground plane antenna. While if we want to have like satellites that cross the azimuth with like a higher gain, like 90, we will have better with a QFH or an Gpredict. So for the purpose of the single reception ground station, I guess what we're going to build here today is it's perfectly fine. So as mentioned before, the ground plane antenna is the simplest antenna we can build, and it's also the cheapest too. The ground plane antenna is made by a monopole and four rods, four radials with an angle form with a ground plane of 45 degrees or different that will give you different frequency, resonant frequency or impedance too. So there are several ways to determine the length of the different elements, but one easy way is use this web calculator from this UK ham radio guy. So we just input the frequency that we want to build the antenna, in this case 435 megahertz. We put the velocity factor of the copper, that is the one that we have, or the material that we will build the antenna. And then that is the material we're going to put. And the velocity factor actually is interesting because the radio frequency current goes through the skin of the rods and not inside of them. So that velocity factor is based on that too. So this calculator assumes like a 45 degrees, but we will see later on that we can actually change that to make better and have a better performance later. So this is okay, but I wanted to go and give you a little bit more details on how to build antennas too. So we are not going to use this calculator, and we are actually going to use, going one step farther here with a simulation, right? This simulation, this shows you a model and a simulation of the ground plane antenna made with open source software called Fortnect2, where there is a monopole that is radiating and receiving the element, and four radials that creates again the ground plane, right? Horizontal or azimuth radiation pattern is omnidirectional, as we can see here. And while the elevation pattern has some gain up to 45 degrees, what makes actually suitable for some kind of LEO azimuth passes too. Regarding frequency resonance, it shows very good adaptations, as we can see in the resonance frequency graph that we can see 435 too. And also good adaptation for 50 ohms too. So what are the dimensions of this monopole, right? So how we can calculate this monopole? So in the bottom, we have like the formulas here. So we have a wavelength of 0.6897 meters, that actually the current measurements for this monopole based on this simulation will be a monopole of 167.3, that is like wavelength divided by 4 times the 0.97, that is like the velocity factor. And the radials are similar, but changing that variable and a different constant, that is the 0.73, that is based on the radials angles that we are going to use. This simulation, the program actually, when I was doing the simulation, I was telling, okay, I would like to have like a 435. So the simulation basically told me you need to put it in 60 degrees. These are the best performance for what you want to do. So with this information, what we're going to do is build this antenna, right? So you already have like your kit. In your kit, we have these options, right? It's a connector, a monopole copper rod, 4 radials copper rod that are pre-soldered, screws and nuts, and 3, and PTG antenna and the mount that I designed for this occasion, right? So the exercise that we're going to have is in the next 25 minutes. I will put also my camera so you can see what we're going to do. And we will first solder the monopole to the connector. Second, mount the radials to the connector to the PTG pipe adapter, and then bend the connectors with 60 degrees. One of the things that I realized is like how we can do 60 degrees in these radials, right? Your phone has, if you have an iPhone or probably Android too, has like a measurement or a level. Try to use that level. Works actually pretty good, like to give you some kind of idea. If it's not has to be perfect, like antennas are not perfect. Let's go for that. So feel free to start doing it. We have 20 minutes to do it, and we are good on time. So. All right, can you hear me well here too? Okay. So I already prepared mine too. pretty much easy. So if you don't have like my third hand like I have, you're probably going to burn your fingers. So if you have some kind of textile or something that you can isolate your hands to, yeah, you can like click your fingers too. But like if you have some kind of like t-shirt or something, will help you to not burn your fingers. Hi Rob, how are you? So yeah, let's get started. Like let me help you with this. You already also have like soldering wire too, so it should be pretty straightforward for you to do it. So I don't know, like I don't know if your kids have. So in this part, it's not working. This?
That's good. It's just weird.
Oh. All right. Okay, so one of your monopoles should have this kind of. Now I feel like a YouTuber or something. So it's a little bit brighter. I made that to help you guys soldering this part. So what we're going to do first is we're going to solder the tip of the connector. Right? You don't have to. You can see, I'm using my flux because you don't have it, but it's okay. Just me for. So I'm putting a little bit of soldering here to help with soldering, right? And then I'm going to solder this part too, the tip of the monopole. No judging, please. All right, so more or less we have these two parts are soldered right now, right? The tip and the rod. So we will go ahead and go for. Thank you. All right, so it's pretty much good. Like, I have been better situations, but this should be good. So if you have something similar as this, it should be good. Okay. So I'm going to give you some time now to do it, and then we can go through it. We can continue.
Not too proud.
So the next thing that we're going to do is mount the monopole with the connector with the 4 radials that you have, right, and the screws. So one of the things that I realized when I was building this 3D model is that the pipe holder or the antenna holder is not very easy if you have big fat hands like mine. So you have to use probably your pliers to set up the nut and then screw it. But here's the final one, more or less. All right. So things going good so far. Oh. There we go. This. We'll type this. Almost done.
What are you all creating here?
We're doing a ground plane antenna. A ground plane. All right. So this is the antenna, right? I cheated you guys a little bit. Huh? Okay, hold on. So I made a little bit of like cheating a little bit, but like because I did this at home, But as you can see here, I made the 60 degree from the prong plane, from the ground plane, and it's what you have to do with your level, okay? All right. So how is everyone doing? All good? Oh, yeah. Okay. Yeah. So Okay, I forgot to mention something. Sorry for that. The pipe, you need to take out the supports of the 3D prints. Is this thing, so you need to take it out like with a plier or something. Enable to use, enable to put the connector, right? Sorry for that, I didn't have the time, but then we will call, they will have like that. Then you can put the connector if you take out the supports, okay?
Slides posted somewhere?
Yes.
Where would they be?
Probably my GitHub, but I will try to make everyone knows about them.
Okay.
Okay, so we don't have a lot of more time, but later after the workshop, if you have any questions, we can go for them too, because there is more content that we have to cover in the next hour. I'm going to measure the antenna, so everything that we built needs to be measured with one device that is called a VNA, right? It's this device that we have right here. This is the device that basically is going to tell us like what is the resonant frequency that the antenna that we just built is going to fall into. Okay, so. So first of all, what we need to do is, sorry for that. All right, so the first thing that we have to do for this Nano VNA is calibrate it for the situations that we have right now. So to calibrate them, we have these three pieces here. So we go to calibrate. So we go to calibrate. We put, let me see where we are. We open, so we need to put like these nuts here that to make it sure that it's an open value. Then a short. So you cannot see this, but use the short nozzle here. And then we put a load of 50 ohms. Then I have to do the short again. And we click done. Save it here, and now what we can do is measure the antenna. So this antenna now is actually suitable for there is like, normally these kind of things are made outside, so there's no radio frequency noise that you can do it, but this is, so do you see the left part of the screen, right? This is suitable for 400 megahertz. I made it in purpose because that means that, as we commented before, as bigger the antenna, the bigger frequency resonance that we have, right? So now we have an antenna that is for 400 megahertz approx. So the next steps that we will do is start cutting tips like 1 millimeter for the monopole and keep going down, down, down with the VNA giving us going through the resonant frequency. So so once we are taking out like pieces of rod from the monopole, we will be moving the resonant frequency, that is the yellow line, more to the right. That is actually going to more than 435 megahertz, right?
What is the frequency? 435?
So we want to, the antennas are made for, or ideally made for 435, but I make actually your rod, your monopole longer, so you have to clip. So then you need to have like the measuring device for that. All right, so let's go a little more definitions of this. We only have 50 more minutes, but I will try to be as fast as possible, right? So let's go for the parts of the receiver. The radio receiver is an electronic device. Is an electronic device capable of transforming radio waves or electromagnetic field captured by the antenna into an information that it can be usable like sound, data, or information. Modern radios are used SDR or software-defined technology. So SDR are a new type of radios where the most hardware circuits has been eliminated, like all the analog parts have been eliminated, and digitalized the signals afterwards. I lost it. So afterwards processing with a dedicated chip or computer, right? Depending on the frequency range, signals coming from the antenna are amplified, then filtered, and if the frequency, for example, is less than 100 megahertz, are down converted to a manageable frequency by the processor with a mixer and a local oscillator too. So that new manageable frequency is then converted to a digital signal with an analog to digital converter to end up being properly managed and processed by the CPU or the other extra chip. For example, in the image that you have here in the left is the internal circuit of the RTL-SDR. That is what we're going to use today. All the process that I just explained is done by the yellow chip, that is the RA20T2, while the digital signal conversion is made by the red square here. So going further, we need to go a little bit more on key concepts of with theory. We need to understand series of concepts that need to be considered to evaluate their performance. One is the frequency range or frequency stability, and this is the range of frequencies that the receiver can receive and the stability of the receiver to maintain a specific frequency too. Then we have the sensitivity. Sensitivity is the minimum level of radio frequency signal the receiver can demodulate. And depending on the modulation type of requirements may be different. For example, the standard is called MDS, or minimum discernible signal, corresponding to 3 dBs signal versus noise ratio, that we will cover a little bit later about that concept too. Then we have the selectivity, is the capability of the receiver to resolve signals from different frequencies. And finally, the bandwidth, that can be adjusted in most receivers to adapt the modulated the signal. In different modulations, the bandwidth is different. For example, in CW or telemetry, it uses 500 hertz, while, for example, TVSAT is for 27 megahertz too. So antennas and receivers not only capture signals, they also capture noise as well too. And this noise can captured by galactic noise, atmospheric Earth and Earth noise due to the heat, for example. Human-created noise like industrial noise or noise created by lightning. If you have you are near a neighborhood that they are using LED lights that create a lot of noise too, and also electronic noise. So every electronic device, based on their architecture with resistors, transistors, they also create thermal agitation of electrons inside of them to just create noise too. So the relationship between the power of the signal and the power of the noise is called signal-to-noise ratio. To receive successful demodulation on the information, the signal from the satellite is sending to us, the receiving system formed by the antenna, the transmission line, and the receiver must provide the adequate signal-to-noise ratio. Depending on the type of modulation used, the requirements of signal-noise ratio are different, as I commented before too. So, as far as the satellites are very far away from us and they don't transmit with a lot of powers, some receivers are not sensitive enough to provide an adequate signal-to-noise ratio. Consequently, they require some kind of help or like an amplifier to boost the signal. As they can add more noise into the system, engineers designed one concept that is called like LNAs or low noise amplifiers that provide gain and a very small noise addition to the with any additional contribution. We have here 3 different types of low noise amplifiers. The 3 key parameters of the LNAs are the NF or noise figure, that is like the contribution of the noise overall for the total noise. Their gain too. Some of them are selective, so they can be filtered, and some others can be broadband. So if you have different frequencies, for example, the NF4L that is broadband can provide gain to all the bands, but in different ways. While the RFK, BFK, and RF designs, or the QNO ones, are selective and provide like more gain in the frequencies that are designed to. So finally, this is important. This is a very important concept. Is we need to understand that in the receiving system, the total noise of the system is dependent of the first gain step after the antenna. Basically, what happened right next to the antenna is what is going to give us like the most effective noise to the entire system. Reason why we need to put LNAs right after the antenna, or having very big cables to don't attenuate as much as possible to prior to put the LNA to. And finishing with the theory, this is the last part. We're going to talk about the Doppler effect. All satellites also transmit the signals in a fixed frequency, but they are moving respect the observer or the ground station with due to the circular orbit around the Earth, right? So the exception of our satellites, as we commented before, of the geostationary orbit. So this relative movement between the satellites and us, the observer or the ground station, produce an effect in the receiving frequency that is changing during the visible path of the satellite. This is known also as Doppler effect. It's the same effect that, for example, we experience when we hear a siren of an emergency vehicle approaching and to us, and when it goes away. So the amount of frequency change is also proportional of the speed of the satellite with respect of us, and the transmit frequency of the satellite. So this is more time for the second lab. Is the SDR, the RTL-SDR tools. So these are a bunch of tools that are designed for this guy here, the RTL-SDR device. So the way that we actually installed the tools, as I commented in the Aerospace Village schedule for workshop, if you have like a Ubuntu laptop or a Linux distribution, you should be able to install these tools with apt installed RTL-SDR. So once it's that installed, we have all of these applications plus the drivers installed to make it usable too. So I'm not going through all of them. It's an exercise that you have for you. You can do it now in the next 5 minutes. But we will talk about one is my favorite. Is the RTL EEPROM, right? That we can actually able to change any part of the memory of the RTL device, such as the serial number. So to be able to change the memory, the EEPROM here. So the next exercise is we have 5 minutes. It's up to you guys. I see that you're still working on the antenna, but the exercise is install SDR and also modify the memory for a new serial number. And yeah, so if you want to go for that, yeah. Yes, so the slides are going to get shared after the today. I will put it on my GitHub, and if you are part of the Discord group of Aerospace Village, I will post a link there too, or I can share it there too. Yeah, no problem with that. There's a channel for resources, I believe. Is anyone doing this, or we can go through other type of demos? Because this is quite very straightforward, so yeah, we can go for more demos. Okay, so here's the solution. Just install it, and the ETL prom is D0. The flag D is because if we have different SDR devices, as I showed it before with my ground station, you have to select which one will be, and then you change the with a flag S the string for the serial number too. Okay, so this is my favorite part of the lab. I think we have 40 minutes, so we're good to go. Is the part of the SDR++. So SDR++ is a cross-platform open source SDR software that I think it's my favorite because it's easy to use and easy to let other people understand about it, right? So one of the features that I like the most is that they have a wide hardware support. It's not only RTL-SDR, it's supported by Aerospace or any SOPI SDRs like RCP1A or any other one, so it's pretty well supported. And another thing that I really like the most is the modular design. So you can design scripts for the SDR++ to do or decode or demodulate some kind of different options if you want to. For the installation, if you go to the sdr++.org, there is the GitHub. So you download the version for this is designed for the Ubuntu, right? But you go to your operating system, download it, install it with the PG, and that's it. If you have any problems on the installation because they require some kind of dependencies, just like the apt fix broke install, they should install also all the dependencies too, as IPT knows what is wrong with it. So, I guess we can go through the application overview demo. I will give you an overview about what is SDR++, okay? All right, so here is SDR++. Let's go through a little bit about the user interface. In the top of the application, we have this button that is like to move in the column of like the options that we want. Play button to start like capturing signals. The mute or like the volume with the potentiometer, and the frequency that we want to capture in this case. This button allows us to center the frequency or have the frequency aside in the signal displayer here. We have also zoom and then the max and minimum for the waterfall here. Okay, so in terms of sources, here is where we're going to decide and show what is the source of the software-defined radio hardware that we're going to use. In this case, I was using TCP, but in our case, we are going to use the hardware that I already bred here. So it's an RTL-SDR, so you will choose all the hardware available. In this case, SDR-RDR. Okay, and then we will choose the one that we the USB device that we want to. This part here is the bandwidth that the SDR is going to look for. So we can actually tell the SDR to capture 2.4 megahertz of bandwidth, and later on demodulate on a small range of that to just like see it more. Or we can decide to put it in 124 megahertz or up to 3.2. Right. So the next that we have here is the gain of the SDR. So we can actually make it have more gain and use like their transistors there and amplifiers to give us more boost of the signal. The IQ correction is to being able to don't see like artifacts in the receiving part too, as well as like the other RTL AGC, auto gain control. I don't use it, or the tuner AGC either. So you can still working on that. You can, if you're interested, but like the RTL AGC, it's better to do it in the gain manually. So the radio part is where we can see here how we can demodulate the signal that we can receive. So we can choose like narrow FM, wide FM, AM, raw, like LSB or CW. We can also change the bandwidth in some of them. So you can add, or as we can see here, we can make it bigger and or smaller, the bandwidth of the demodulation of wideband, right? We have the option of recording. If we're going to see the path and we want to record in the baseband or like the audio of the signal, we can go through that. We can save some frequencies in SDR++ so we can go directly to like the NOAA 15 frequency and capture that information and capture that. Or we can, and then we can have like the sync here. It's how we want the applications to send us the data in form of audio, or in form of network to connect it to another service that could probably use that information to other purposes too. We have also the module manager here, so we can add or make our own script modules, and a RigCTL server that actually helps with the Doppler effect, as we will see later in Gpredict too. And let's go through one test here. So I selected the source, RTL-SDR, and there's what we here see. So these are all the signals captured by the SDR here. Probably is a lot of noise. Actually, do you know if there's the AMSAT simulator here? Probably. So this is what we will capture, right? It looks like there's a lot of noise, or I don't know what it is, but this is how we'll. I brought my AMSAT simulator too. What we can do here is connect it to it and see. what we have. And I believe it's 439.4. Yeah, we can see here some signals. But it's like in this type of conferences, it's very weird it's very hard to try to discern between what is a signal and what is noise too, because there is a bunch of people. But if you put your signal, if you in your ground station, you shouldn't have all of these. And we will see it later, unless we want to do it now. But so let me start these. So I just started one of the AMSAT simulators here, and we started with see something. Yeah, it's a lot of okay, so how many of you are using the computer to do this? Because what we can do is up to you guys. We have 30 minutes, and I can go through Gpredict and how to track the satellites in my workstation in Florida, connected over VPN, and you can see full procedure of that, or you can play with this the next 10 minutes, and later we can go to Gpredict theory and I can show you. It's what is you up to guys for? Gpredict? What did you say? Yeah. Okay, I can do that. Okay, let's do that. Let's do that in that way. Let's do that. Okay. So let's talk about a little bit of Gpredict. All right. So basically, Gpredict is like a satellite tracking software that is real-time tracking software, an orbit prediction application, and it can be track a large number of satellites and display their position and other data in list. This is the definition of what they have in their website, right? So if you're interested, the way to install it is apt install Gpredict, and what we're going to do is the overview on that. So it's also available for Mac and Windows too. In this way, I will do it with my host Mac here, as is actually easier. All right. So this is Gpredict. So in Gpredict, what we have is a couple of parts of the interface. In the top side is where we are going to see the satellites moving around and see the area that is going to cover, right? And in the down part is information about satellites here in the right, and also the azimuth and elevation pattern that we have here, as we commented before, right? In some of them. So for you guys, prior to give me a sec. I don't see it.
Yeah,
Hacker's gonna hack, bastards.
what?
Just me and Seth. All right. If this doesn't work, I have another option too. Okay, so going back to Gpredict, the way that we need to do is like configuration of our ground station, basically telling him what is our location or where is our antenna is going to be located. So here we need to basically go to preference, edit preferences, and in the ground stations, we have our address or location. So we will need to add a new location. Here, Vegas, we have two options. We can select an option here in the United States or any locations that we want, or we can use latitude and longitude of that location too. The next that we have is like the TLA updates or the Keplerians of the satellites that we have. So this is the TLA resources that the application is going to use to understand where the satellites are going to be in the sky. So you probably are going to see these TLA resources. The ones that are from Telestrak are actually not updated. They changed the domain. Instead of .com is actually .org. So when you arrive home, just change the .com from .org and should be good for you guys. So give me a second, I'm going to try to connect to my phone. And we should have good. All right. Okay, so the next thing that we have to do is once we added the TLE, so the Keplerians, we need to add create a new module and a satellite and add the satellites, right? So for that we will create a new module in this game, and we're going to call it DEFCON 2, and we will put our home location here as we will look for that particular So I'm going to add some satellites or spacecrafts out there, like the ESS is one, the NOAA 15, the NOAA 15 is another one. Let's put the 18 and 19. I think we put some ham radio 2. All right. Okay. So this is what situations we have right now, okay? The next thing that we have is the map. In this map, we will see the movement of the satellites. As we can see, the ground track goes to east to west, or west to east, depending on the aircraft or the spacecraft. And then we can see satellite info, for example, like their orbit, or also the transponders that they're using too. So it's going to be good for us later on to select this transponder information and put it and feed it to the SDR++, so it's easy to get. Okay. Let me see something else. The next step that we can do to here is see the next pass for this particular satellite, the SO15. So we can see the pass of the polar. So we know that if there are actually, this will be the pass, and this will be the graph for that pass. Like, remember that when we select the ground station, that like the ground plane antenna was good up to like 45 degrees, is the elevation of this. So this will be a nice pass for our ground plane antenna because it's the gain that we have in lower than 45 degrees of elevation. It's suitable for this pass too. So other options could be, other situations could be that the pass is making a big mountain here, making that the satellites is actually very polar, so it's very vertical from us. Meanwhile, this one is actually going in an orbit that are going to be less than, I think it's 15 degrees. So that will be suitable for our ground plane antenna. So if you have like other antennas, like a quadrilateral antenna or the egg beater, their patterns are a little bit different and allow them to have like better elevation gains up to 90 degrees, right? So that will be better for passes that are on top of us too. So the other things that we can do with this software is we can see here when is going to be the next pass, right? The next pass for the next pass where all the satellites that we have here are in 2 hours. So I don't think we're going to have time for see any other ones, but we will see. Like we can go through other technical stuff too. Going through a little bit down, we can see the information about. We were selecting the SO50, right? We can see the azimuth at that time, the elevation at the specific time and the on time, the speed, altitude, Doppler frequency. Everything is in here, right? So it's our variables that are going to be helpful for later understand where. What the satellite is doing and how we can receive those signals too. And one of the things that I really like too is how we can cooperate or relate Gpredict with SDR++, right? So there is there's like some preferences that we can do here in Gpredict that is part of the interface, and we can actually tell Gpredict connect to my server that is in Gpredict that is for the RigCTL that is basically going to change the frequency of the satellite, of the transponder of the satellite, and modify that frequency with the Doppler effect that is also calculated by Gpredict. So how we can do that? We basically have to add a new radio, in this case SDR++, in the local host, or we can have another client-server architecture too, with a port, right? So if we go back here to I'm basically changing the TCP, the RTL TCP because I'm already connected over VPN on my house, so we are going to be able to suit my TCP. So it's going to be on localhost, or you can actually let's do it in this way too. It's like also good. So here, RTL-SDR, we go to the RigCTL server. It's listening, right? The status of it's listening. So if I want to start tracking one satellite or the frequency with the Doppler of the satellite, in this case the SO50 or the IAS, we go here, radio control. And we have the radio control of the SDR, right? So what we can do is track the target that we want to track. We click it on track, and automatically Gpredict knows that we are going to track this spacecraft, and we can engage the SDR++. And as we see, right, in top of this is the frequency that is the satellite transmitting, but is being changed by the Doppler effect. And this number, this frequency, is actually sent to the SDR++, as we can see here too, right? So $432. So that means that while we track with Gpredict, we are telling SDR++, hey, change the frequency so I can understand via Doppler effect what you are trying to send.
It's updating the Doppler effect continuously as the satellite changes.
Correct, yes. It's every time changing. Right now, we don't have a way to test it out with receiving because there is nothing out there. But if you follow this procedure, you will have your frequency moving in the spectrum and the SDR following that changes directly, so you don't lose any information from that capture.
It's targeting one of those cubes that over there.
Yeah, the CubeSat, yeah.
That's integrated.
For the next. I tried. I had this, but it didn't work. There is a lot of noise here, so it's like kind of like it's hard to identify them.
In the bar, what would a like strong signal look like?
So a strong signal will be looking like the red one.
So it'll be like a strong.
The strong signal, actually, like it depends of the modulation. For example, if you are sending voice, you will see. Let me show you. Something like this. Something like this. Right? So you have like as red as possible is like stronger than this. But there's other ones, for example, you have APT signal waterfall that are like this one. Too. This is what the NOAA satellites are using too. Or there are other digital modulations too. There's LoRa too that are based on the spectrum modulation too. So I have a couple more slides to cover, and it's expanding the ground station. So with the information, I gave you a lot of information. I know there's a lot of theory, but once you have some time to recapitulate the slides, another thing that you can do with this information is expanding what you did here. Okay, so we can expand to LoRa modulations or to decoding with another project that is called TinyGS. You can install TinyGS in a LilyGo device. Is a microcontroller that you can use it, and it's pretty straightforward and it's automatic. You don't have to do anything. You just put it there and make it easy. So I think it's this one. So TinyGS is not this one. If you are interested, is I believe it's this. So is this device here like here, right? So this device will do basically all what we captured today, like receiving of the signal, decoding of the signal, etc., etc., etc. We can actually also automate this tracking and the capture by using SACNOX. That's another open source platform that you can have it connected to the internet, so other people in the world can have access to your ground station to make listenings. And it's very good for like universities that they need to have like telemetry information from their satellites. It's a very cool project. You can actually decode manually recording signals that I explained it using SATAM. And also use of, if you want to make your ground station a little bit more complex, but having efficient on how many antennas you want to have, you can actually add duplexers or power dividers that will help with this. So you can use one antenna to multiple SDRs and or multiple devices or multiple antennas for one device too. That is what the duplexer will do, and the power divided will be different, same antenna, two different devices. Right? There is a cost of this. It's you are going to lose power of the signal. So you are adding noise to the overall transmission, but I think it's worth it. And finally, client-server ground station architecture. So you can have your ground station with a Raspberry Pi connected out there, and then connected to your Raspberry Pi, as we saw that I was doing too. And finally, use the SigDigger. SigDigger is another open source platform. It's similar as DS++, but it's like super powerful. It's developed by one of my friends, Batsrek, back in Spain. And it's more like a signal analyzer, so has a lot of potential. There's it's like insane, it's massive. So if you can have like the option to and you like signal analysis, I will recommend using that one. And yeah, that's it. Thank you very much for attending today to the workshop. I'm glad that you did your antenna. I hope you learned about that. I would like to thank you also the organization for helping me and all the volunteers for today. And finally to my father, Alejandro Fernández Ponce, A4 Bravo Florida Kilo. He's the one that helped me also be motivated in ham radio and this kind of radio stuff. And I just put also some slides of references. So all the information that I tried to condensate in these slides are here, are 3 reference slides. But go, hold on. This is one. Next? Okay. I will post this like in 30 minutes. So. This is another one. And this is the last one. Yeah, no. Yeah, thank you very much for coming.